Let's do another example, finding the eigenvalues and the eigenvectors of a 2x2 matrix. And let me just tell you, this time we'll end up with complex eigenvalues. So check this out. Here we go. We want the determinant of a minus lambda times I is equal to 0. So I just need to go to the diagonal and then subtract lambda from it. And then keep the rest. And then make this equal 0. And then work this out. This times this, we have 1 minus lambda times 3 minus lambda. And then minus this times this, which is negative 2. So that will make this plus 2. And that will be 3 minus lambda minus 3 lambda plus lambda squared plus 2. And that's equal to 0. And we have lambda squared, and that's minus 4 lambda plus 5. And that's equal to 0. Right here you can try to use the quadratic formula. Yeah, but since this right here is an even number, it will be easier if you use completing a square. So lambda squared minus 4 lambda, move the 5 to here, so it's minus 5. Now take half of this, which we get negative 2, square that, we get positive 4. So we have to add 4 to both sides. And then we can get lambda minus 2 squared equals, this right here is negative 1. And then continue. Take the square roots, both sides, plus minus, cancel. We can see that lambda is equal to, bring the minus 2 to the right hand side, we have 2, and then plus minus, and we have square root of negative 1, which is going to be the I. So we have two lambdas. Lambda 1 is 2 plus I, and then the other one is 2 minus I. Now, if you have seen my previous video, the bonus part, then you know there's a quick check to see at least if we have made a mistake or not. The check is, if you add this and that together, we get 4. The sum of the eigenvalues is 4. And if you go back to our original matrix, if you do the trace of it, we just do the diagonal and add them up, 1 plus 3, and that's equal to 4. So if you do this quick check, at least you'll feel a little bit better about you are at least on the right track a little bit. But as I said in the previous video, if somehow you end up with lambda 1, lambda 2, and you get like 5 and negative 1, add them up, you get 4, and the trace is also 4, unfortunately. But anyways, this are actually correct. Now, let's see how do we find the corresponding eigenvectors. Here we go. First, I'm going to let our v equal x, y. And then we will start with the first lambda, which is 2 plus I. We go to the diagonal and subtract lambda from these entries. So we are looking at 1 minus, put parentheses around it, 2 plus I. And then the rest stays the same. For this diagonal, 3 minus 2 plus I. And then we multiply that with xy. And we want this equal 0. Okay, so this right here is negative 1 minus I, and then negative 2, and this is 1. This is 1, and then minus I. And we have xy equal 0, 0. And then let's just go ahead and work this out. So this times this, and this times that. That is equal to 0. Continue, x, and then plus 1 minus I times y, it's equal to 0. So right now, these two equations, they look very different. But the truth is, this is just a constant multiple of that. If you would like, you can multiply the second equation by the positive version of this, which is 1 plus I. And you see, they will cancel to 0 once you add them up. And 1 plus I times 1 minus I is positive 2, so they cancel. So we can just pick one of the equations. Let's use the second one because the coefficient here is just 1. So we see that x is equal to, move this to the other side, negative 1 minus I times y. That's the connection between x and y. So now I'm going to pick 1 for y, then we will see that x is equal to -1 minus I times 1. Distribute it, we get -1 plus I. So our corresponding eigenvector is equal to -1 plus I and then 1. Yep. Now for the second eigenvalue, lambda 2, and that's just 2 minus I, which is just a complex conjugate of the first eigenvalue. And I will leave this to you guys. You guys can go verify on your own. But the truth is, the second eigenvector corresponding to that is going to be -1 minus I and a 1, which is just a complex conjugate of that. So here we have it. Eigenvalues and eigenvectors. That's it.